Let U and V be vectors in Rn. The inner product or dot product is written U dot V and calculated by U transpose times V. Let U be a 3 by 1 matrix or vector, and V be the same, different numbers but same dimensions. The dot product of U and V is calculated by U transpose times V. If you take vector U and lay it horizontally, that's its transpose, and then V stays vertical. 2 times 3 plus negative 5 times 2 plus negative 1 times negative 3 comes out to negative 1. If you multiply in the other direction and calculate the dot product of V and U, or V dot U, then it's V transpose times U. Take matrix V, lay it down, that's its transpose. Vector U will be vertical, 3 times 2 plus 2 times negative 5 plus negative 3 times negative 1, and that also totals out to negative 1. Dot products can be done in either order. You get the same result. The length or norm of vector V is written with a set of double bars, and it is the square root of V times V. Now, it's easier to look at it this way, so let's take just some general vector V in R2, and we'll just call it AB. Then this will look more familiar. It is basically the Pythagorean theorem. The length, it's also called magnitude, of vector V is the square root of a squared plus b squared. So it's pretty much like finding the hypotenuse of a right triangle when you know the two sides. A unit vector is a vector whose length is 1. If you divide a vector by its length to create a unit vector, then you have normalized the vector. Let's take an example. Let's let vector V have the values 1, negative 2, 2, and 0. Find a unit vector U in the same direction as V. Now that's just fancy language to say normalize. So if you're going to normalize a vector, you're finding a unit vector that points in the same direction. First step is to find the magnitude or the length of the vector given. Let's take each value, square them, add them together. Feel free to use your calculator. I would hold off on the square root to get a total underneath. So 1 plus 4 plus 4 plus 0 totals out to 9. That number is not always going to be a perfect square, so it's a good idea to get the total, and then if it happens to be a perfect square, great. You can square root it and get an integer. They're not always going to work out that way, and we'll do an example or two of when it's not. Now to normalize, we're going to take vector U, and we're going to normalize it as 1 over the length of V times V. Alright, so our length was 3. To normalize, we're going to do 1 over 3 times vector V. Recall this can be written vertically in vector form as a matrix of 1, negative 2, 2, and 0. Just list the numbers vertically. 1/3 times each value will give you a vector that points the same direction as the original, but only has a unit length. Let W be the subspace of R2 spanned by the vector X, which is given as 2/3 and 1. Find a unit vector Z that is a basis for W. Since W consists of all multiples of X, you can create Y equals 3X, 3 times vector X given, So that's going to be 2 and 3. This is just to ease the calculations. You can stick with the original numbers, but if you use a scalar, that new vector will also be in the subspace. That's just one of the properties. Okay, so I chose to multiply by 3 because I knew it would cancel that denominator. Now let's find the length of this vector 2, 3 that's a little easier to work with, and then we'll normalize it. So remember, y is 3 times x, and that gave us the vector 2, 3. The length of vector y is the square root of 2 squared plus 3 squared. Well, 4 plus 9 is 13. And here's the reason I said hold off on your square root, because sometimes you wind up with a number that's not a perfect square, and that's okay. Now, we were asked to find a unit vector z that's a basis for w. So that means we're going to normalize vector y. 1 over the length of y, that's 1 over square root of 13, times y. So remember, vector y is 2, 3, write it vertically. And so you have 2 over square root of 13 and 3 over square root of 13. This vector has a length of 1, and it points in the same direction as x and y. And so it will serve as a basis for w. For vectors u and v in Rn, the distance between those two vectors, written as dist or distance, abbreviated for u and v, it's the length of the vector u minus v. In other words, distance from u to v, the distance between them, is the magnitude or the length of the vector u minus v. Example, compute the distance between the vectors u, which is given as 7, 1, and v, which is given as 3, 2. Now, if you're finding the distance between two vectors, first find the difference between them. 7, 1, 3, 2. Finding the difference gives us a vector 4, negative 1. Now let's find the length of this vector. 4 squared plus negative 1 squared, all under a square root. That's 16 plus 1, which is 17. Square root of 17 is the distance between vectors u and v. If we move up to vectors in R3, these up here were R2. If we move up to R3, the distance between two vectors, which is still given as the magnitude or the length of vector u minus v, subtract based on position. So we'll take u minus v squared from the first entries, and then u2 minus v2, that's the second entry, subtracted, squared, and then finally u3 minus v3, that value squared. Two vectors are orthogonal. We're used to hearing the word perpendicular. It's just another way to say that for these two vectors. Two vectors are orthogonal if their dot product is 0. Another way to check is if the magnitude of the sums of your vectors is equal to the magnitude of each one separately squared and added together. It's the Pythagorean theorem version of it. Either one is fine. You can check this way or just check the dot product and see if that's 0. Example, determine if vector u and vector v are orthogonal. Now these are 3-dimensional vectors, so it's a little bit hard to visualize a 90 degree. Let's go back to the original definition, and when we compute the dot product of u and v, we'll actually calculate it as u transpose times v. So let's take vector u, transpose it or lay it down, and v will remain vertical. So u transpose times v, 12 times 2, plus 3 times negative 3, plus negative 15 times 1. So we have 24 minus 9, that's 15, minus 15 is 0. And if your dot product comes out to 0, you can say yes, your vectors are orthogonal to one another. And since this section's fairly short and mainly calculator based, I want to go ahead and sneak in a couple of extra examples. Let's find a unit vector in the direction of this 3 entry vector. So this will be a vector in R3. I'm going to go ahead and write that vector as in a horizontal form, just to make it easier to see that when you calculate the magnitude or length, it's each entry squared and then all added together. This one has a length of square root of 1650. 1650 is not a perfect square. I typed it into my calculator and I think I got 40 and some change. So what I did was I looked at a largest perfect square that divides into this evenly, and what I found is 1650 is equal to 25 times 66. I played with my calculator a little bit. So 25 square roots to 5, the 66 will just stay under the radical. So this is the length of the vector given up here. Now to normalize that, or find a unit vector that points in the same direction, I'm calling it vector z. It's 1 over the length times the vector. So 1 over 5 square root of 66 times the original vector. Well, if we multiply 5 times this fraction, the 5's will cancel, and that leaves 1 over square root of 66. 40 over 5 square root of 66 is 8 over square root of 66. And then finally, negative 5 times 1 over 5 square root of 66. The 5's cancel, leaving a negative 1 over square root of 66. A second example of distance would be find the distance between vector x and vector y. If you're given two vectors and asked to find the distance between them, subtract their values first. 12 minus negative 1, that's 13. Negative 6 minus negative 8, that's positive 2. And then find the length. 13 squared plus 2 squared, that's 169 plus 4, which is 173, all underneath a square root. Again, get the grand total before you attempt to square root. I had no luck finding a perfect square other than one that will divide into 173 evenly, so I left the radical just like it is. I didn't try to simplify any farther. I hope this helps. You guys let me know if you have any questions. This is the first of 3 sections in the last unit. You will find these notes in your Google Drive folder, so let me know if you need anything or need any help.